So I know that this becomes square root of t to the fourth plus 3t squared plus 1, evaluated -1 and 1, like that. Plug in 1. What do you get? Root 5? Minus, plug in -1. Root 5. Zero? So what is the conclusion? Given any vector field over any curve, the work is always 0? No. No. That, again, it's just to make this problem work out pretty nice. If you were to change the curve again and only do like half the parabola, go from 0 to 1 instead, your answer would have been in root 5. If you want to include more of the parabola, your answer is going to vary, right? I need to change those examples. I need to make them, I don't like the fact that they both turn out to be 0. I'm not happy about that. Any questions? Man, it's already 10 after. Now, just a little notation for you. There's an equivalent form of this line integral of the vector field. So this is the way that we say work, right? This is work, but if you see this, it is equivalent to this. So this is where we're saying, where are we going to see those come into play? Here it is. If your vector field has p, q, and r as its component functions, then if you take the line integral along C of the scalar function p with respect to x, so you're just looking at that one with respect to x, then add to that this one with respect to y, and then this one with respect to z, that is the same as doing this integral. So sometimes it might be a little easier for us to use the other version. All right, now this is a problem I took out of the book, and I know for those of you who've taken physics, you may have seen something like this, and there may possibly be an easier way to do it, but let's just stick with what we're doing in this class right now, okay? A 180-pound man is carrying a 20-pound tool bag, walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured in foot-pounds. Also, weight is a force. Okay, so your weight on a planet is a force. I hope you've learned that your mass is independent of... so, okay, all right. So everyone okay with the idea that weight is force? All right. So here's the picture. Here's the silo, like my silo. There it is. It's a 90-foot silo. It's got a 20-foot radius. And this man is going to walk around, go up with his bag all the way to the top. How much work did he do? So if I know this is going to be a work problem, right? Then what are the things I need? Work is going to be equal to line integral over C of f dot dr, right? So I'm going to need to know what is the field, right? What is the vector field? And I'm going to need to know r, which is the path function. So what would you like to talk about first? Which one are you most comfortable with at this point? You want to do r? Okay. You got to draw me this thing, right? Let's see. 1, 2, 3. Like, oh man, that's terrible. Seemed like at the end things went bad. Well, whatever. Okay. I have my computer drawing. It's even better. All right. So the guy goes around 3 times and he gets up to the top, right? Can you draw me that thing? I can give you some hint. If you look at it this way, it's just what? A circle. And what's the radius of that circle? 20, right? How would you draw a radius 20 circle with some sort of vector function? If I just asked you to draw me a circle, radius 20, you would do what? 20 cosine t, 20 sine t. But that would draw me just a circle on a flat sheet of paper. I actually want it to come up, right? Okay? So I'm hearing t. I'm almost there with you. Okay? Almost. Here's the kind of catch to it. I'm going to put right here question mark for a second. Right? Let's think about this. This component of the vector function tells me how high I'm going to be, right? So if I put t there, as I don't know if this is going to work, what is my restriction on t? Well, if you're going to use t here, it's got to be 90, right? But there's a problem with that. You need to draw 3 complete circles. So that's going to be the thing that's going to control your t. How do you draw 3 complete circles? Because that's what it says. He goes around 3 complete revolutions, right? What does your angle have to vary between? Because look, you're using trig functions, cosine and sine. What are you going to do to get 3 full revolutions? 0 to 6 pi, right? That's what has to be here, the way it's written. So this cannot be t, or else you're going to be 6 pi high. 6 times pi is about, yeah, it's not 90, is it? So that's not quite going to work. Understand? So, but you're on the right track. It's just it can't just be t. So what do y'all think? Think this through. At t equals 0, where do you need to be in terms of height off the ground? 0. And at t equals 6 pi, you need to be where? 90.
15 over pi t.
You're already reduced, right?
90 over 6.
There you go. Okay, we'll start with that. You want this 90 over 6 pi t. Look at this. That's what's going to go here. Now let's talk about y. At t equals 0, where are you? 0. So you're 0 height, right? At t is 6 pi, where are you? They cancel and you get 90. And this is linear, which means that as you go around, you're going up at the same rate, right? It's a linear incline. Does that make sense? Yes, go ahead.
Number I just passed over my head. Where'd you get the 90 from?
Oh, the silo's 90 feet high.
Oh, that's right.
Yep. Make sense? You could almost do it this way. If you kind of uncoil that thing and straighten it out, you know, if you uncoil it and keep its angle, that's the blue thing, but straightened out, you know this has to be 90, right? But the question is, how long is this?
It's 3 times the circumference.
Three times the circumference of one circle. What's the circumference of a circle? 2 pi times r is the circumference of a circle. R was, so 40 pi is the circumference, and then do what? Divide by? No. Multiply, divide? Is that going to work? No, that's not going to work. I'm trying to make a connection that would be easy. It's not going to work that way. Because you would need the actual arc length
Yeah.
to get this side. Or I'm sorry, to get this distance. So let's not mess with that. That'll get uglier than it needs to be. I think just looking at this, most people can see the relationship. You need it to be linear because you're assuming the stairs are going up at the same rate the whole time, right? And you need it to be 90 at 6 pi and 0 at 0. So that'll work. All right, so far, is that all right?
Yeah.
Okay, now we'll need the derivative of this. Reduce the fraction, right? If you reduce, 6 goes into each of those. So 15 over pi t. Joel, is that the way you did it? How do you reason it the same sort of way?
Yeah,
Okay.
kind of that way.
All right, so we'll need the derivative in the integral, so I'm going to get it now. Derivative of this, negative 20 sine t. Derivative of that, 20 cosine t. Derivative of that is just 15 over pi. I need the field. What's the field? 0, 0, negative 180. Where are you getting that from? So the only thing we're assuming is acting on this guy is a gravitational force, right? But it's him in his bag. He had a 20-pound bag. 200, right? Yes? Negative. Okay, so negative 200 or positive 200? What do we want? Does it matter? It depends on what you're saying here. Do you want to know the work done by gravity, or do you want to know the work done by the man? You see what I'm saying? The force downward is gravity. He has to overcome that force going up, right? So he does work, right, which you could consider like positive work, or negative work would be the work done by the gravity. Make sense?
Yeah. What is
So-
0, 0 again?
Okay, so why is it 0, 0? We are assuming here that when you look in three-dimensional space, like in this silo, right? This vector is pointed straight down, right? That vector is pointed straight down. We're assuming gravity is straight down. The negative 200 is his weight plus the weight of his bag. Understand? Now, we know that in reality, it may not be completely straight down, depending on where you are on Earth, but for this problem, it's good enough, right? Okay. All right. Good? That's it. That's a pretty easy field, isn't it? That's a pretty easy field to work with. And I think most of you know from physics that you really only had to ever pay attention to his upward, that you didn't need to take into account any of this motion left and right. It's purely just the up and down opposing the force of gravity that matters. But we're going to see that in our formulation right here, aren't we? When we dot this with this, right? Because these first two components are 0, it's going to kill these two, right? Regardless of what they were. So it actually doesn't matter how he went up the silo. It's the fact that he got from the ground to 90, which is going to give you the force. Does that make sense? The left and right, front and back motion didn't matter. Just up. But do y'all see what I'm saying? I'm trying to get you to see that this shows you why it doesn't matter. Okay. All right, so I'm going to go back to this. This is, I know I'm going from 0 to 6 pi. I'm doing my force, right? My force with this curve plugged in, but my force doesn't have any variables, so I don't plug anything in. Dot that with 20, this one, negative 20 sine t. Did I say dot with that one? I think I did say dot with that one. I meant to point to this one. I'm sorry. The same thing, though. It kills off these pieces. So all you're left with is this. 20 cosine t 15 over pi dt. And what do you get? Negative. Ooh, negative 3,000 over pi, right? I'm integrating that from 0 to 6 pi dt. And this just becomes negative 3,000 over pi t evaluated from 0 to 6 pi. Why is what?
Why is it 6 pi, the upper bound?
Wasn't t from 0 to 6 pi?
We said
Seen what?
we said 15 over pi t.
No, 15. It was 90 over 6 pi t was the z component of the curve. Then the derivative of that was the z component of the derivative. But then the t restriction was from 0 to 6 pi. Yeah? Okay, now we plug in and we get what? 6 in there to cancel. Negative 18,000 minus 0. And what would that be measured in? Well, because we're measuring the silo in feet and the man in pounds, this would be, work would be foot pounds. So foot pounds. Foot pounds. That's the work. Sorry? I think it is. Yeah. All right. One more. I have enough time. I like this problem. There's going to be in the homework for this section, which I know all of you are going to do. They're going to have, there's quite a few word problems in this, or not word problems, but just more like this stuff towards the end. So just be prepared for that. A 10 kilogram object moves with a position function. R of t is sine 4t sine 8t t squared with t between 0 and 1. Find the work done on the object during this time period. Any ideas? Well, they want to know what work is, right? Okay, so we're going to need R, but we have it, and we're going to need R prime, right, to get our formula. So work is going to be integral, line integral, f dot dr like that. R is given to us by, like we didn't have to work for it, did we? It's there, it's provided. It's nice. I wish everything were free. I wish everything was just given, right? Okay, so you want the derivative? What's wrong?
You're like, I wish everything was free. I'm like speaking away
Oh.
stock grades.
4 cosine 4t is the derivative of this, right? And then 8 cosine 8t is the derivative of that, and then this was 2t. So I'll need that in my formulation for this, right? Anyone notice something's missing here?
The field.
The field, right? But like last time, what we did is, well, the man was 100 and something pounds, and we just said that the field was this thing. What's the difference between that and this? We have 10 kilogram object. That's his mass. So, or that's not his, it's an object. I don't know if it's a he or a she or if it's anything. It's 10 kilograms, right? It has mass. Mass is not a force, right? Mass is not a force. So right now the field is still a question mark, isn't it? The field is still a question mark. I need a field though, and for a field, I'd like to, since I'm talking about work, I'd like to see what the force vector is, right? So how can I get force if all I have is mass? So this is, again, some physics. Force equals mass times acceleration, right? Acceleration. Yes? You agree with that? But, if I have, when I say acceleration, it's the acceleration of the object, not the acceleration of gravity. It's the acceleration of the object.
So we take the second derivative.
There you go. So look, if this is your position function, the first derivative is your velocity function, the second derivative is your acceleration function. So if I want to know what the acceleration of this object is, I take its second derivative, which is because this was velocity, right? So I take the second derivative and I get negative 16 sine 4t. And then I do derivative of this and I get negative 64 sine 8t. And then derivative of this I get 2. That's your acceleration function. Then if I want the force as a field, it's the mass times the acceleration function, which is going to be, well, mass is 10, right? Multiply this by 10, it's a scalar. So you get negative 160 sine 4t, negative 640 sine 8t, and then 20, yeah? There's your force.
Could you just pull the mass right out of the
Pardon me?
Could you just pull the mass right out?
Yes, you could have taken the mass out of the whole thing. But if it was not given, like if they said the mass of an object is m, you would want to pull that out. If it's 10, then you may as well keep it in. But you can take it out. It doesn't matter. All right, so all I need to do is dot these. What dot these? I said these. What do I mean? I need to dot my force with r prime. But what? Good question. Don't you need to plug in the r into this? Well, this is already in terms of t. So we don't need to do that. It actually came from that, right? But so we're good. We just dot those two together.
Yeah, that's why I said go ahead.
Do we have a restriction on t? It was given, right? 0 to 1. Dot, dot, dot. Here we go. So this times this. So negative 160 sine squared 4t. Right? Oh, I'm sorry. Who? I don't know why I pointed up there. This times this. Negative 640. Is that right? 640. Sine 4t cosine 4t. Y'all good with that? Here and here. Then I got to go here and here. Maybe we should have pulled that 10 out. What is this going to be?
Negative 5,120.
Negative 5,120. Sine 8t. Cosine 8t. And then finally, 20. That one I don't mind doing. 40t. And then dt. How are you going to handle this right here? Sine 4t, cosine 4t. Double angle formula, turn that into what? Sine of 8t, but half of that? So scale to 640. I hope everyone's comfortable with that. These are those little things that I do that I just don't know. I remember as a student like not knowing how the teacher did something, and here I am doing the same thing. This is negative 320, what, sine 8t. Okay, I'm going to have to stop. Negative 320 times 2 sine 4t cosine 4t. That's this right here, right? Nope, not distribute. Then this, using the formula, is sine 8t. So go back and look at your double angle formula. Sine 2u equals 2 sine u cosine u. So that's your double angle formula, but replace that with 8t. And then this one, same thing, right? I can do the same on that. So minus, what's half of that? 2560 sine 16t. And lastly, 40t. I don't have to change that. And then I get to integrate. Am I out of time? No? Okay. So we get to integrate. Go ahead and integrate that. I'm wondering if I took this problem out of the book. I thought maybe I had taken this problem out of the book, but I don't see it in here. All right, well, it is what it is. Y'all, what did you get? You got a final answer?
Yeah. Well, I mean.
What did you get?
For the integration or for the?
Like everything?
Oh.
No? I thought you were saying you got everything. Y'all think y'all could do that from there?
Oh yeah.
Okay. All right. You get the idea, hopefully. All right. So just so you know, last night I was going to grade your test, honestly, the ones you had turned in. I sat down, and that's when that hailstorm came in and just ruined my night. And so I don't have those for you. The ones you just turned in today, I've got to grade those also. But I'm giving 2 exams tomorrow for my Cal 2 and for my college algebra. I promised them I'd have their tests graded by Friday so that they could drop if they needed to. So that basically what I'm telling you is that I'm not going to get to yours until this weekend. My intention is to have both your mini exams back to you Monday, and then I'll give you your new one. I believe the new one will be the last one. All right? We're good? We start 13:3 next time. We're doing good time-wise, I think.
So we made up for that one day.
I don't know if we made up. All I know is we have 1, 2, 3, 4, 5, 6, 7 more sections, and I think we have more days than sections still.
Have 4 more, right? 4 more days?
Till the end of the semester?
Without the,
Is it 4? No, it can't be 4.
or it's just 2?
I hope it's 6.
I thought.
We don't have 2 more weeks left. Is that right?
I thought this was. I thought,
think
yeah,
we
but
have
I thought we
3.
have 2 more weeks left.
Hold on a second, man. When's our last day?
It's May 13th, I think.
It's early, man.
No, it's not. That's late. We have the 18th, the 20th, the 25th, the 27th, the 2nd, and the 4th, and that's it. So we have 6 more meetings,
We have 6 more meetings?
6 more class meetings, and then the final is the week after that. No. Well, we're not. I'm saying I have 7 sections to cover in 6 days.
Oh, okay. Cool.
It's going to be tight. It's going to be real tight. Live streaming, yeah.
Oh, hey, you know.
I usually just barely am able to touch the last section. But the last section's really clean. It's just like, here's a formula. Boom. Like we get to a final result and it's good.
You know that girl in our FQ, the tall one? Yeah. She's gonna do this